Today we are going to discuss a lengthy problem based on the concept of instantaneous center of rotation. It comes under a combination of translational plus rotational motion of connected bodies of a combination of translational and rotational motion of connected bodies. So what are the simple examples of connected body? A very simple example is a rack and pinion arrangement in which there is a rod which is connected to a cylinder and there is a collar over here which is free to slide along this axis. So as this particular cylinder rotates to the right, this particular rod starts moving upwards and you can see that this particular block starts sliding to the right. So this is known as a rack and pinion arrangement. It is found in railway engines. That's a very common example which is found in railway engines. Now these are two connected bodies. Our aim is to find the linear velocity of one of the bodies when rotational velocity of the other body is given. And for this we are going to use the concept of instantaneous center of rotation. So before I define a problem, let me quickly explain what is the instantaneous center of rotation. Let us consider a circular body which is rolling without slipping. This is the velocity of center of mass. Each and every point on the body will have same translational velocity, say v. However, at this particular point there will also be a velocity due to rotation, and suppose omega is the velocity of rotation, we have a relationship v is equal to r omega. So in addition to this v, there will be one more v, and when the body is rolling without slipping, velocity of center of mass is same as r omega. So total velocity here will be v plus vca, and that will be 2 r omega. Look at this particular point. The transitional velocity is r omega to the right, but you can see that at this particular point the rotation is in this direction. So the velocity due to angular motion will be in this direction. The two velocities will cancel each other and the net velocity of this point will be 0. As the net velocity at this point is 0, we can assume that the entire body rotates about this point, and this is known as ICR, the instantaneous center of rotation. The net velocity is always lying on the line which is perpendicular to the instantaneous center of rotation. So if you consider this as a radius vector, then this vector which joins the ICR with the point is always perpendicular to the net velocity. For example, suppose you want to find the velocity at point P, and suppose this is your instantaneous center of rotation, say I, then you join the radius vector IP. The net velocity will be perpendicular to IP. So this net velocity will always be perpendicular to IP. So don't forget that at any point you want to find, suppose this is point Q or suppose this is point Q, the net velocity at point Q will be perpendicular to this. Now please note, this net velocity is a combination of rotation as well as translation. So you can see here the translational velocity is r omega in this direction, the rotational is like this or upwards, It depends upon the direction of motion, and accordingly you can find out that the net velocity is always perpendicular to the vector which joins the point and the ICR. So this is the concept of ICR. It can be proved. If you want a detailed explanation of ICR, you can see my lecture on rotational mechanics. I've explained the concept in detail. Now, before going into too much of theory, let us directly go with the problem so that I can make you understand the concepts in a much clearer way. So let us see the situation. This is a horizontal rod, and on this horizontal rod there is a collar. This is a cylinder. Center of this collar is joined to this cylinder at, say, point A. Let us take this as point B. This particular cylinder is rotating about a central axis at 420 RPS. Of course, it is not omega, it is the RPS. We are supposed to find the linear velocity. Obviously, this body will move to the right as the rod rotates to the right, cylinder rotates to the right. As a rack and pinion arrangement, this particular particle will move to the right. So it will make a to and fro motion. We are supposed to find the velocity at point B, that is VB. It is given that this AB is 1000 millimeter. It is given that the radius of the crank is 250 millimeter, and we are supposed to find the velocity at B when this angle is given to be 30 degree. It is given that the angle is 30 degree, and we are supposed to find the velocity of B under these circumstances. There are two approaches to this. One approach is a simple approach of ICR, approach number 1. Approach number 2 is a vector method. A vector method is slightly complicated, but will have a understanding which is much simpler compared to ICR, but many students can find ICR also simple. So let us try to understand the concept of ICR, how to draw ICR of combined motion between B and A. So we will draw ICR for B also, and we will draw ICR for A also. So let us try to do that. Now I am drawing a situation here. This is a block A having velocity VB, whereas this is a cylinder, and at this point the velocity is, of course, since it is purely rotational motion, velocity of A is perpendicular to this. Now this body is performing purely translational motion, so the net velocity of this body is VB. There is no other velocity. So ICR will lie along a line which is perpendicular to VB. So let me draw a line which is perpendicular to VB. At the same time, VA is the net velocity, because there is no other velocity over here. VA is equal to R omega, if this is R, and this velocity is at right angles to the radius. So obviously ICR will be perpendicular to VA again, so it will be along OA. So if I extend OA, it will meet here somewhere. I hope I am able to draw a straight line, but please bear with me. And this is the ICR of A, and this is the ICR of B. ICR of B lies along this line, ICR of A lies along this line, so obviously the common ICR I is this. Now for VA, the radius vector becomes IA, and for VB, the radius vector becomes IB. Now we have to use geometry, pure geometry, to find the lengths of IB and IA. So let us see how to do that. I'm joining this. B and A we are joining. Let us do the calculations. Let me draw a right angle here. Say M. This is 250. This angle is 30. This is 1000. So if I draw, use sine theta is opposite side upon hypotenuse. If this is 250, AM will be 125. Right, now let me find this angle. What is this angle? You can have cos theta equal to adjacent side upon hypotenuse. Sorry, it will be sine theta opposite side upon hypotenuse. I missed it. Sine theta will be opposite side upon hypotenuse. So that gives you theta as sine inverse of 0.125. Let me calculate that. That is 7.1 degree. We can take it approximately as 7 degree. So this angle is 7 degree. Okay. Now I want to find, of course this angle is 90. So this whole thing is 180 degree. If this is 7, this is 90, the sum of these two becomes 97. This angle becomes 180 minus 97. Sorry, 90 minus 180 minus 97. That is 83 degree. Correct. Now this angle is 83, this angle is 60. I hope you are following this. This angle is 83, this angle is 60. So the net angle is 83 plus 60. This angle will be 180 minus sum of these two. So it will be 180 minus 83 minus 60, and that will be 37 degree. This whole angle is 90. Out of that 7 goes, so this will be again 83. This is 83, this is 37. Of course this angle is 30, this angle is 90, so this angle will be 60. So this is the way we have computed all the angles. I hope I am clear in the geometry. It is not a difficult task to do. You can directly get this as no need to do so many complications. In fact, if this angle is 7, this angle turns out to be 83. This whole angle is 90, this angle is 30. That makes this angle as 60. Once you get this angle as 60 and this angle as 83, it is very easy to get this angle as 37. It is your choice. Whatever you want to do, you have to find these 3 angles. After we find these 3 angles, we are going to use sine rule. And what is the sine rule? Opposite side upon sine of angle. So 1000 upon sine 60. Will be same as opposite side, say IA upon sine 83 and is equal to IB upon sine 37. So let us quickly do this calculation and get the values of IA and IB. So please do the calculation and let's see what is IA and IB. I will be $694.9. It is $695. $695 and IB will be, sorry, this is IB. IB is 695 and IA is 1146. 695 and 1146. So let me redraw the figure now. Let me draw only points. This is point B. This is point A. $695, 1146. This is I. This is VB. VA. VA is at right angles to this. VB is at right angles to this. Now, this radius vector can be used now to obtain relationship V is equal to R omega. So VB will be R for VB is IB into omega plus. Please note that this omega will be between A and B. So it is a relative velocity between A and B. So VB will be IB into omega AB and VA will be IA into omega AB. Now out of that we know the value of VA. VA is R omega, for which R is 0.25 and omega is 2 pi n. So 2 pi n is given 420, but it is RPM, so we have to divide by 60. IA is 1146, that is in meters, 1.146 into omega AB. So let us compute omega AB now. So let's do the calculations. 9.6. So omega AB, I am getting 9.6. Let me substitute this here and I will get the value of VB. So VB will be 9.6 times 695, that is 0.695. And that is 6.67. You get the value of VB as 6.7 meter per second. So this is the simple approach of doing this sum with the help of instantaneous center of rotation. There is a vector approach here, but it is going to be complicated and much lengthier. It is much better to use the approach of ICR. The only point we need to understand is that the ICR always lies along the line which is perpendicular to the net velocity. The common ICR will be obtained by joining the two lines and finding their point of intersection. Thank you so much.